Okay, so I just gave back the exams. Everyone's doing really well. So, and I understand there's a question or two about the homework assignment today. It's this, I think, figure 5.28. I have it up on the board here. I think this is what you're supposed to fill out. So now here is the main idea. The main idea is that the machine, we know now all about what an instruction is at level ISA 3, right? It's binary, yeah? And it's stored in memory. And the way it executes is the von Neumann cycle. Fetches, what does the von Neumann cycle do? Fetch, decode, increment, execute, repeat. And so it fetches that, and so it has to fetch a binary, you know, machine code that it brings into the instruction register in the CPU and execute it. So that means that it cannot execute a program written in C++. It cannot execute a program written in assembly language. Before it can execute any of those programs, what do they have to do? They have to be translated into machine language. Well, what if you have an assembler or a compiler? Because what are you, look, imagine this. What are you guys going to do? Remember what our big project is going to be?
You're going to use a higher order language.
You're going to use Java, the higher order language, to translate
assembly language
to machine code. And you understand that when you get that machine code, it's going to be in that hex string format, and you're going to be able to, you know, in order to test your assembler, you could just copy and paste it into the object code thing and then load it and run it. It has to be in that hex. Are you with me on this? Mm-hmm. So here, the whole idea about this problem is, well, so how are you going to run your Java translator? What are you going to have to do with that? Compile. You're going to have to compile that first to get it into machine language so that it can do that. That's what this problem is all about. That's all this problem is doing. It's making sure that we understand how to analyze a situation where we have translators that are written in high-level languages that then need to be translated before they can take another program and translate it. Are you with me? So that's the whole idea. And so if you understand the process and you can imagine that process, there's only logically one way to fill out these boxes. And what's the key concept? The key concept is that the program that's running in that middle box, because what does that middle box represent in figure 5.28? That's the CPU executing a machine language program. So that letter A has to be a what?
Machine language.
It must be a program written in machine language. I think the best way to analyze this is when you describe the file, you can say, this is a program that does blank, written in blank. See, look, if you say, I don't know, let's just say Q is a program to do, X, and it's written in Y. Right? Now, if you take this program to do X and it's written in Y, and if you put it through a translator that translates from Y to Z, are you with me? So if you take this, and you put it into a program that translates from Y, let me see, that translates from Y to Z, you know, if you put in this, then what's going to come out? Tell me in English what's going to come out.
Q.
No, it won't be Q anymore because Q is written in Y. But what will come out? A program to what?
To do
that does X.
That still does X, but it's written in Z. A program, what's going to come out is a program a program to do X written in Z. And I think if you see, this pen is lousy. Oh, that's pretty rare. Hey, wait a minute, what are you agreeing for? What's that?
1 for 2.
Oh,
You missed the last one.
I missed. Oh, you're keeping track. All right. Okay, so is that, you see how that works? I mean, it's the same. It's a program that does the exact same. And now that you have a program to do X written in Z, you have to think, okay, so now what can I do with this in order to get my result? So there's a sequence of steps that need to be done. And you can, if you figure, the main thing that you can't do is you can't put a program there in that middle box in figure 5.28 unless it's written in what? Machine language, machine code. And I think if you just keep those rules in mind, there's only one way to figure this thing out. This is a really nice problem. I admit to getting this book, this exercise from a very old book back in the 60s or 70s. And I saw that exercise and I thought, wow, that is just very illustrative of this whole idea of translators and compilers and assemblers, and so I adapted it. And I think it's really instructive. Okay, are there any more questions about the homework today? We actually have homework due today. I'm hoping we can finish chapter 5, and if we're lucky, we'll be able to start chapter 7. So let's go back and look at what we did. If there's no more questions, let's go back and look at what we did at the end of class last time. This was before the exam, so I don't know if you can remember that far back. But do you remember this figure 5.21? Do you remember this program? What we did is we had this program up on the screen, and we actually hand translated this into assembly. Let's take a look at, remember what the first, how did it work? Can you, here, let's look up figure 521. What's always the very first statement? Branch to main. And then what did that char ch, what was that?
Char would be a symbol, or ch would be a
Symbol,
symbol.
ch colon.
Right.
And then for
A
dot block 1, because it was 1 byte, and then for the J
dot block 2.
Yeah, so J colon dot block 2, and now here we have main colon, because that's where we branch to, and then and the first statement in main was what? Character input, ch direct, character deci input, or deci J direct.
Load the accumulator.
Yeah, load the accumulator.
J direct.
No. Oh yes, load the accumulator J direct. Add accumulator 5 immediate. Store accumulator J
Load
direct. Load byte.
accumulator.
Add accumulator 1. Store byte.
And then
ch direct, right? Store byte ch direct, right?
And then string output.
And then string out. Oh no, not string output.
It'll
A
be
character output for the ch, and then a caro with the new line character, and then a deso, and then another new line. Yeah. So we see how to translate that. Now, what I would like to do now is and then I think what we did is we looked at this second half of figure 5.21, and we verified that in fact, we just verbally went through all that code. There it is. But now there's one little feature here that I want to show you. I want to demo this actually. And there's one little feature that I would like to show you here. It's this, do you see up there where it says ch, okay, first it says branch to main, then it says ch dot block 1. Now, do you see the comment up there under on the line on the ch colon? It says global variable. Then what does it say after that? Pound 1C. All right. And then on the one that has J, the one that has the symbol J, it's at address 0004. It says dot block 2, but now it says global variable #2D. Okay, so here's what those things are. Those things are kind of important. They're going to be kind of important from now on. This #1C, this is called a trace tag. Okay. And this pen is not very good either. Oh, that's better. Oh, okay, what's my score now? Okay, so this is a trace tag, and what you should do, this #1C, what this means, the way to read this is, okay, first of all trace tags start with the symbol pound, okay? And furthermore, they are contained in comments. Now, because it's contained in a comment, what does that mean about the execution of the program? Or the code generated or whatever. It does not affect any of the code generated, and because it doesn't affect any of the generated code, it doesn't really affect how the program executes. Okay? But what it does do is it allows us, this trace tag allows us to do a graphical debugging of what's in memory without having to refer to the memory dump. And it's really, really slick. As a matter of fact, from now on, I think once we get at this point, from now on, I don't think you'll ever really need the memory dump again. You probably won't need it again, because these trace tags are really a much better way to trace what's in memory. And so, and what this means is this #1C, this means 1 byte character. So this means 1 byte character. All right? And what is that other one? Next to the
2 bytes.
Yeah, so that's a #2D. Okay? So what this means is 2 byte decimal. And what I want to do now is I want to give you a demo and show you what in fact happens whenever we single step through the program and we have these trace tags in our program. Okay, so here we go for a nice demo.
It said something about the trace tags for the homework that's due today.
Yes, in fact,
To use those.
from now on it's required that you use trace tags.
What if I already turned it?
I know.
Well, you should, well, okay, this time. But, you know, theoretically.
Okay.
Okay, so here's our demo. And as usual, we have this slick little help system. We can go to 5.21, which was our program. And here's the program that we saw up on the screen and in the book. And right here are these trace tags, which is what we're going to demo. So here's the #1C, and what do we say that stood for?
1 bit or 1 byte character.
1 byte character, and this #2D stands for 2 byte decimal. Now you see, and then the assembler, when it scans through a comment, what it does is it looks for these pound characters, and anything that starts with a pound, it assumes that that's a trace tag. And so, and then what it does is it detects, I mean, because you're saying it's a 1 byte character, what it will do is it will take this symbol, CH, and it will use the symbol, it will use this symbol here to label the memory location. And then this #2D, because it's on this line that has a symbol J, it will take this J and it will use it to label the memory location where the J is stored. Okay, and this number so the C means to display the content as a single character. The D means to display the content as a decimal, and the number says how many bytes to show, how many bytes to show. So this one here has to be consistent with this one, and this 2 right here has to be consistent with this 2. All right. So now watch this. So we'll copy to source. I think you're going to like this. Okay. And so what we will do is first of all we'll build a symbol. All right. And now watch this. Because we have these trace tags here, watch this. We're going to start debugging. Oh, and by the way, the input is M and 419. Okay. And so watch what happens when we start debugging. Boom. Check this out, sports fans. What we have here is, if we were to have a runtime stack, the runtime stack is going to be here. And look at this. Now, what's the C++ memory model? Stored in a fixed location in memory. So instead of going over here and looking at the memory dump, what do we have? What is this? 0003, what is that? That's the address of this cell in memory. But what do we have over on this side? That's the symbol. Are you with me? That's the symbol. And over here, what is this? 0004? That's address in memory. And what is this? That's the symbol. All right? Now watch what happens whenever we single step through this. So we're going to single step through it. Okay, so the first program that's going to execute is going to be branch to main, right? So this line, I mean, the fact that this is highlighted means that that's the statement that's going to execute next. And then once we single step, it will fetch that, put it into the instruction specifier. So after we click the button, this branch is the statement that just executed. Are you with me? This one is highlighting the statement that will execute next. Yeah. And let's take a look. And what is the value in the program counter? 006. And why is that? That's because this is the statement that's going to execute next. Does everybody see that? How that works? But now watch this. Check this out, you guys. When we do a character input into CH using direct addressing, what's going to happen down here? Are you ready for this? Drum roll. Boom. Yeah. Highlights it, shows you what its value is. Okay? And then we and now we just did the character input, so now what are we going to do? Decimal input. So what's going to happen when we do a decimal input? 419 is going to go into J. Check it out down here. Cool, huh? All right. And now what statement's going to be executed next? Load accumulator, so that J is going to be loaded into the accumulator. What do we have in the accumulator so far? 0, Zippo. So now when we do this, what's going to happen? Boom, the 419 goes in there, which in hex is 01A3. Are you with me? And now we're going to add it. We're going to add accumulator. So boom. So we added 1 to the accumulator, so that is 424. Or no, sorry, added 5, which is okay, 424. And now and what's going to happen next? We're going to store. So we're going to store that. And look, boom, it shows you right there symbolically. So you can see that, oh, J, this is the current value of J. You don't have to go refer to that ugly memory dump. And it shows you, it labels it here symbolically. So it's a symbolic debugger. Okay? And now what's going to happen next? Load byte accumulator, right? So the accumulator gets that the 4D, right? And then adds it, makes it 4E. Are you with me? And now when we store byte accumulator, we're going to store it into CA. So what's going to happen here? Yeah, it's going to change to int. Now, why is it doing it? How does it know to have this be a character, whereas have this to be a decimal? Why is it the character? Because what did we say here? We said up here, we said display this in character format. You see what I mean? So the assembler took this and it knew how to do that down here. That's how it's tracing it for us. Okay, and then boom, and now we'll do character output. So out came the N, out came the new line, out comes the 424, and then we stop. Pretty slick, huh? And what's going to happen is, in the future, whenever we write our programs, and we have local variables and parameters, well, it'll all come up here on the runtime stack. And we'll be able to see the stack without just looking at that memory dump, which would be very tedious to do, and our stack will be labeled with the symbols from, using the trace tags from our assembly language program. Okay, so that concludes our demo. Okay, so that's the story of how trace tags work. Now, the other topic that I want us to go over now is the concept of a symbol table. Now, actually, you told me on the exam what's the difference between an assembler and a compiler. It's where they translate from, right? So what does a compiler translate from? From higher language level 6, whereas an assembler translates from assembly 5. Okay, now we know about the concept of a symbol table at assembly 5, right? The symbol, we went over that in detail, and the value of a symbol is the address of where it's going to be stored. But now you see, you can imagine that for a compiler to translate from a high order language, it has to have a symbol table also. But the main thing that a symbol table has at the compiler level that a symbol table at the assembler level does not have is it has the concept of type. Now let's think about what a type is. You know, there's really no types at assembly language, at the assembly language level. Everything is just binary. In fact, it is so type free that we can even have programs that modify themselves. We can, all it does is fetch, decode, increment, execute, repeat. That's all the von Neumann cycle does. And it can do that it can fetch no matter if the data, no matter if the bits in there were stored in there as if they were data. I mean, it can treat data as programs, it can treat programs as data, much less it can treat, integers as reals, it can treat reals as strings of characters as, I mean, there is no type. There's no type checking at all. So the whole concept of type is unique to level 6. That's one of the things that level 6 has that level 5 does not have. And the way it has it, so what is it that gives us types at level 6? It is the compiler. Do you see what I mean? The compiler is the program that creates for us types at level 6. And the way it does it, so if look here on figure 5.22, the way it does it is it stores, when you say here in this program, when we said char ch, when the compiler goes through and scans that char ch, what does it notice ch is? It notices that ch is a type char. So what it does, not only does it store the symbol, so look at this figure, not only does it store the symbol ch, yeah, and its value, which is, what is the value of the symbol? 3, and what does that represent? A memory location of where that's going to be stored. But it also stores a third thing, a third attribute, which is what? The type. So you see, like, if you can imagine, if you are instead of writing an assembler, if you were writing a compiler, you would have to keep track of what type it is in your program. Your compiler program would have to keep track of what the type, each of the types of each of one of those items is. You see what I mean? And so you would probably have, you remember how enumerateds work? Enum? Yeah. Come on, you guys remember enum. Remember we had red, black tree, and enum was red. One value was red, the other value was black. And we had black and white and gray, and so so it would be like one possible way to do this is you could have an enum. An enum if the variable that you just scanned was a character, another enum if it was a double, another if it was an int, another. You see what I mean? And the compiler then would keep track of what the types are. Now look, in this particular example, in the program in figure 5.22, everything that this compiler did, everything that this program did was legal, right? And how did the compiler check that everything was legal? Well, you see where when it got to the place where it said j plus gets 5. Well, what it did is the program now wants to add 5 to j. Yeah? So what it does is it goes down to its symbol table and it says, oh, I see from my symbol table that J is of type integer and its addition is legal for an integer. So then it goes ahead and allows that translation. It goes ahead and translates it and it's legal. But look at this next example. Suppose that you want to do, now what is this percent operation?
Mod.
That's mod. Now what does mod mean?
Remainder after
Division.
Yes, it's a remainder when you divide, right? So if you have a variable that is type float or double, what does that mean? That means it's a real number with what? With a fractional part, a decimal, right? Mm-hmm. Okay, so what would happen is the compiler would come along. So here's some fictitious program. Okay, so the compiler would come along and when it gets into J, it would in its symbol table it would say, oh, J, that's of type SInt. And then when it gets to float Y, it'd say, oh, Y is going to be a real number with a decimal point. So it would store that the kind as S float, so that would be an enumerator for that. And then look what would happen. If it ever gets to a line that says J gets J mod 8, is that 8? Mm-hmm. Yeah, J mod 8. It would go down to its symbol table and say, oh, here's, what's the type of J? And we're looking at, it would consult its symbol table and it would see, oh, J is of type int. You can take a mod with an int. So it would generate the code for that. But then if it ever got to a line like this that says Y gets Y mod 8, it would go down to its symbol table and say, oh, wait, oh, okay, let's find out what Y is. It would go down to Y and it would look up, oh, that's a float. Oh, and the compiler, the compiler writer, the person who wrote the compiler, would have built into it the fact that you can't take you can't do the mod on a real number. And so he'd program the compiler to generate a compiler error at that point. Are you with me? So that's how types are implemented in a compiler. Types are implemented at the high order HOL6 level by the compiler by imposing these rules, and those rules have to be written into the compiler, written into the translator, the allowable operations. And the way they enforce type safety is by having all those rules programmed into the compiler to restrict the programmer from not doing illegal operations. Is everybody see how that works? Okay. And then the next few slides are just some information about trace tags, which we already looked at. There's actually two different kinds of trace tags. There's format trace tags and symbol trace tags. And the only ones that we need to use with global variables are the symbol trace tags. We'll see about format trace tags, how to use format trace tags later. Okay. And oh wait, I take that back. I said that backward. We used format trace tags. We did not use symbol trace tags. Symbol trace tags are not required for global variables. It's the other way around. Okay. So what we used were the format trace tags. And here, the ones that we looked at here were the £1C and the £2D. Here's a list of all the legal ones. You can say £1C for a 1-byte character, £1D for a 1-byte decimal. Those are the ones we used. And then you can do £2D for a 2-byte decimal. I'm sorry, we did £1C and £2D. You can also do £1D for a 1-byte decimal. You can do £1H for a 1-byte hexadecimal and a £2H for a 2-byte hexadecimal. So if you use the little H there, then what would come out in that little cell? It would just be written in hex. So it formats. That's why it's called a format trace tag. So it would format it however you want to format it. Is everybody good? Okay. So 4 more instructions, but we already know how they work. There is an arithmetic shift right instruction. So you type that in as either ASRA for arithmetic shift right accumulator or ASRX for arithmetic shift right index register. And we already know how arithmetic shift rights work, right? If you do an arithmetic shift, oh, it was. Well, the translation of it.
Yeah.
So yeah. But now you remember what does arithmetic shift right do?
All the bits get shifted to the right.
Yes, and what is that mathematically?
Divide by 2.
It's divide by 2.
And take the floor.
And what?
And take the floor.
Oh, right.
To take the floor.
Right, right.
Oh, right.
I was like, take the
You have the floor now. You can take the floor. And then here's, I don't know. You know, if you look at 0098, oh, by the way, it's a unary, right? Because it just takes what's in the register and it just does it. So there's no, it's a unary operator. So 0098 turns into a 004C, and then arithmetic shift left does the same thing, but it does left. Oh, by the way, let's take a look at this. Now, what is this called at the bottom of the arithmetic shift left instruction slide here? What is this RTL? And RTL stands for what?
register transfer.
Register transfer language. And do you see how it's specified in RTL? C gets R sub 0, so that's the leftmost bit. Okay, and what does the comma mean?
Then
No.
No.
at the same time.
At the same, simultaneously, what? R 0.14 gets what? R1.15. And the comma means what? At the same time.
15.
Yeah, yeah. So all of those things get shifted in parallel without ever being lost. I mean, nothing ever writes over another one, you know, in the process of the shift.
Yeah.
And then NCB.
Yeah, and then the semicolon means after that happens, then n gets, you know, 1 if r is less than 0. Where r is the content of the whole register considered to be a signed quantity, and z gets r equals 0, they're all zeros, and v gets the overflow. And then we also have a rotate left, and we had pictures of rotate left before, and here we have a rotate right, and that's okay. And now, so the main ones that we want to know how to use there are the shift ones, because those are arithmetic operations that are useful in translating arithmetic statements that do arithmetic in a higher order language. Okay, but now comes a pretty big concept. The concept of a constant. Now we're going to learn a new pseudo-op.
Great.
All right. Now, do you remember one of the things that we said at the very beginning is we said, what is, when we were learning about symbols. So, you know, here when we said main colon. And then down in the symbol table, we had symbol, and then we had value. And then the symbol here would be main, and what did we always say its value was?
It's the memory address.
It's the memory address of where the first byte of this code is going to be stored. So we said, so what did we say? The value is the address. The value of the symbol is the address. Okay, well, guess what, you guys?
You lied?
I lied. Well, if I said always, I probably did not say always, but here's one exception. And the dot equate is the exception to the rule. Okay, it's like English. You know how many exceptions we have to English rules. There's exceptions all over the place. So, what the dot equate dot command does is it has to have a symbol in front of it, but dot equate does not generate any object code.
It changes how the symbols are interpreted.
What it does is it equates the number after it to the symbol, and no object code is generated.
Which means it doesn't even take up space in memory.
It doesn't even take up space in memory. All it is it's a notation for the assembler. You see what I mean? And that's an important concept. It doesn't take up space in memory. It doesn't generate any code. Is everybody with me on this? Because here, suppose you said dot block 5, what would that do? What code would that generate?
Generates 5 bytes.
5 bytes of code. What if you said dot word 5, what would that do?
2 bytes.
2 bytes.
2 bytes, and it would be 0005.
Yeah.
And dot byte 5, what would that generate?
0.
1 byte.
1 byte, and it would be 05. It would generate. But what about dot equate 5?
No.
It would not generate anything.
Wouldn't work if we didn't have a symbol, would it?
And it wouldn't work if you didn't have a symbol. Yeah. Okay. So dot equate does not generate object code, and furthermore, the value of the constant symbol is not an address. Okay. So now, with that in mind, we're going to do another little exercise. Let's take a look. Now here, I think it's important to zoom in. From now on, I think we need to do a little more, zoom in a little bit farther. Because what I want to do is we want to have this up here and this here at the same time. Do you see what I mean? So, all right. So here is a program, and let's see if we can generate the
Machine code?
well, not the machine code. We'll generate the assembly code.
Oh, let's see.
All right. Are you with me? Okay. So what's the very first one?
Branch. Main.
Branch to main. Okay. Now, what do you suppose this next one is? It says now it's const int bonus equals 5.
Symbol's bonus.
The symbol's bonus. Okay, so here's bonus. Oops, I guess it's lowercase, right?
Can we just dot equate 5?
Yeah, bonus colon, and it's dot equate 5. Right. All right? Now, what about the next one? Int exam 1. So what would,
Exam 1.
so that's exam 1 is the symbol.
So we will dot block.
Dot block what? 2. Are we done with this line? Nope.
Does dot block 2 and dot word 0 do the same thing?
Yes.
Okay.
But we're not done.
We're not done. Because we want a trace tag.
Because we want a trace tag. So what should we put here? Well, let's document this. Let's say global.
Global variable.
Let's say global variable.
Is that required for the trace tag?
Well,
Or is it just nice?
it's just nice. I'm not going to be... Okay, but now what is our trace tag?
2D. Yeah.
Pound 2D. Okay, now what about the next one?
Exam
Exam
2.
2.
Mm-hmm.
Dot block 2.
Dot block 2.
Global variable.
Global variable
2D.
pound 2D. Okay, so here. All right. And then what?
Score.
Score. And what is that?
Dot block 2.
Dot block 2. Global variable. Another pound 2D?
Yeah.
Pound 2D. And then what's next?
Main.
Main.
Main. And then what?
Deci.
Deci. Deci what?
Exam 1.
Exam 1.
Correct.
Exam 1 direct is right. And then what?
Exam 2.
Deci.
Direct.
Exam 2 direct. Is everybody good? Okay. And then what?
Load the accumulator.
Now, haha, load the accumulator.
With the button.
Yeah, with what?
Exam 1.
We have to do exam 1 first, right? Exam 1 direct. And then what?
Add.
The accumulator.
Add accumulator.
Exam 2 direct.
Exam 2 direct. Good deal. We're on a roll here. Okay.
Check shift right.
And then ASR. ASR what? The index register or the accumulator?
A.
A. Yeah, are we good? Because that's doing what? Dividing by 2?
No.
And what do I put here?
Nothing.
Nothing because it's unary. Okay, and then what?
Add the accumulator.
Add accumulator. Now comes my question.
Bonus immediate?
Who? Now, why did you say immediate?
Because bonus is 5.
Yes, because this equates bonus to 5, and so that's the point.
Great.
Do you see? Because the code that's going to generate is add accumulator, and then whatever the value of this is, which will be 5, and then immediate. Is that cool? Now, did everybody see that? Why that is? Yeah, that's very good. Okay, and now what?
Store the accumulator.
Yeah, store the accumulator where?
Just to score.
STA to score. Score. Direct, and I think at this point we can, the rest of it's pretty, this was the main thing, yeah?
I have a question.
Yeah.
If we were to translate this directly to like assembly language word for word, would we end up...
Oh, this is assembly language.
Would we end up getting a character out end line at the very end?
What's your question?
Because of the end line at the end of the CF.
Yeah, and this, yeah, we have...
Last statement B.
Yes, you need to do, when I ask you to translate that, if that has an inline there, then the compiler will do character output, quote, bash, quote, bash, n, quote, comma, immediate, yeah. Yeah, because otherwise it won't go to the start of the next line before it does the next output. Whatever it is, I mean, you know. Okay? And then, so here, let's see, did we get it right? Here's the listing from the, check our work here. Are we good? I remember we did this once before and we weren't right. But were we good? All right, so that's, oh, you guys are good. And here's the, oh, now check out the symbol table, you guys. Look here. What is the value of exam 1 on the symbol? 0003. So if we come back here and we look at exam 1, where is exam 1? That code is generated at 0003. But if we come over here and we look at the value of bonus is at 0005. But now let's go back here and let's take a look at what's generated at bonus.
Nothing.
Oh, there's no code. There's not even an address there. Do you see? No code was generated for bonus in that column.
So when the assembler puts it together, it puts the value of bonus down where we called it in add-a. That's the only.
Oh yeah, look, good point, good point. So now let's take a look at the instruction at address 0016 where it says add accumulator bonus immediate. Do you see why did it do 700005? Because the value of bonus is 5. It equates to 5. We equated it to 5. And now you see why, now when you see that 0005 there, and the fact that that's immediate, you see that it actually takes that constant 5, boom, and puts it in.
So where do we need to use equate and not?
Well, equate is used with constants. This is the use. This is its use.
And
so constants don't have to take up space somewhere to do a direct, you know, it can just boom right there, immediate.
So is that just an easier way of doing? We could have just said, you know, add immediate 5 immediate, but this is just an easier way to keep track of everything.
Right. Okay. Oh yeah. Because here, why do we give it a symbol? Because it corresponds to our C++ program. You remember? So bonus is the identifier of the constant. And remember, we said we wanted to have the symbols in the C++ program correspond to the variables. And now we see that a symbol can correspond not only to a variable, but a symbol can also correspond to a constant. And so we want it to match this. Is everybody good? Okay. Actually, I think, and this just, other figure just shows that it's possible to put that stuff at the bottom of the program, but we don't need to do that. Okay, well, I was going to start the next chapter. Oh, actually, we'll end with this little announcement. Okay, now, what we're going to do now is we're going to take a break from assembly language programming because you guys have this big project, right? It's to write an assembler, to write a translator that translates from assembly language to machine language. So what we're going to do is we are going to temporarily skip chapter 6 and we're going to jump ahead to chapter 7. So we're going to branch to 7. Okay? And the reason we're going to branch to 7 is because 7 is about language translation principles. And what you're going to do is translate a language. So what we're going to do is we're going to learn about some grammar theory, and we're going to learn about some finite state machines, and we're going to learn how these theoretical concepts are used to help us write our translator. Okay? And then so the plan here then is we'll go to chapter 7, we'll get through chapter 7, and we'll get started on the project, on the translation project, and then we'll jump back to chapter 6, and then as you are working on your we will be going through the material in chapter 6 at the same time you're working on your project, so you'll be doing those in parallel. And that way we'll have enough time to be working on your translator so that it won't all be crammed up until the last, the last few weeks of the semester. And I've got milestones for you to finish, so everything will be, smooth. Yeah, it'll be smooth. We won't be all crammed up at the end, I promise you. So we have these milestones, but in order to do that, we've got to get you started on the translation project right away. So tomorrow, I'll see you tomorrow, and we will start chapter 7. Okay? Good deal. See you tomorrow.